get started. 10 o'clock. Welcome, everyone. Thank you for coming to my talk, Practical Computer Science, What You Need to Know Without the Degree. Thank you for coming after a keynote. You're all jazzed up to kick off 2 days of learning. My name is Pat Viafor. I work here in Huntsville. I'm a software engineer. And I'd like to tell you a little bit about myself. I love learning, passionate about programming. I'll program for 8 hours during my work day, then go home and program some more. I have both my bachelor's and master's in computer science. Hopefully that means I know what I'm talking about. We'll see. I've been working as a software engineer for 10 years, so I've been doing this for almost about a decade now. I'm the organizer of Huntsville Pi, right here in Huntsville, our Python meetup, our local meetup. And I like speaking at conferences, otherwise I wouldn't be up here in front of you guys. But only one of these things I feel really define me as who I identify with as a software engineer. It's not that I enjoy speaking at conferences, that's fun, but I do it like once a year. This is only my 4th time speaking in front of a conference crowd such as yourselves. It's not that I'm a Huntsville Pi organizer. I've only been doing that for 2 years. I don't identify as that. Oh, is it the thing that I've been doing for 10 years? Not necessarily, because even if I weren't working in a software engineering job, I'd still be going and doing it at home. And you know what? Those degrees don't matter. What matters is that I love learning and I'm passionate about programming. And what you might be saying is, wait, a CS degree is not important? That's all I hear about when I go apply for jobs or I go to job fairs. Hey, are you computer science? No, I'm not. Oh, sorry, no thank you. So people think, oh, a CS degree is this vaunted prize to be won. At SIG CSE, Computer Science Conference, there was someone who went and interviewed a whole bunch of employers there and said, hey, how do you feel about computer science degrees? And what that employer said is they put an emphasis on soft skills over the computer science degree. Can you work well in a team? Are you dependable? Are you reliable? While prized by employers, a CS degree ended up not being a must-have. Now that's not to say, some employers will say you need a CS degree. I may or may not disagree with them depending on the work they're offering. If it's a web startup, maybe you don't need that CS degree. Some people might just not know what they're asking for. And that's because a lot of people don't realize just what a CS degree entails. So I'm going to open this up and tell you a little bit about what sort of courses my CS degree was. When you hear of somebody with a computer science degree, what do you think that they are good at? Shout it out. Math. What else?
Writing software.
Writing software. Anything else?
Solving problems.
Solving problems. All good answers. A lot of people start off with saying programming. I've had so many people think, oh, you're a computer scientist, you must be a really good programmer. So I started breaking down my coursework into what I felt were my programming classes. The top is just a representation of my undergrad, the bottom is a representation of my grad classes. It turns out that only about 14% of my undergrad were classes aimed to teach me programming, 9% in my grad degree. Some people might say, okay, well, it's not programming. You surely must know how a computer works. Well, I did take some courses of how a computer works, but not a large percentage. Now, in my grad degree, I actually went back to go learn more about how computers work. I did not get a whole lot. Only 10% of my undergrad was how computers actually work. How about language design? Who's going to write the next Pascal or the next Lua or the next F# or insert language of the day? Well, I took some courses on language design. Not a lot. Not most of my course was language design. Software engineering. How do you architect software systems for the long term? I had a focus in software engineering in my undergrad. I was dual majoring for a little bit, computer science and software engineering. Then I got a job and said, you know what, this dual major maybe is needed. So I took a lot of software engineering classes, but still not high numbers there. 14% of my undergrad. Math and theory, that's the first answer we've heard. This is actually where the bulk of my coursework was. 27% of my undergrad, that was the highest percentage of my undergrad, was math and theory. You may look up here and say, hey, algorithms and data structures, databases, AI, those are programming classes. You should go put those in the programming column. Where I differentiate between those is, yes, I programmed in those classes, but the goal of that class was not to teach me programming. I was not graded on how well of a program I had and how clean code I was. It was whether I could apply an idea. Who here has taken some sort of history course in like grade school or high school or most hands go up? In a history course, you have to write essays, you have to answer questions through writing, you have to express your ideas through writing, you have to parrot information through writing. A history course is not a writing course. Writing is how you apply that information to show that you've learned that information. Similarly, with a lot of computer science classes, it's not that it's a programming course, this is how I apply the math and theory I'm learning behind computer science. And for those of you who like graphs, this is actually a breakdown. We have all my electives, because undergraduate degrees have so many electives that you just have to fill in, or things like your sciences, your literature, your civics classes. But the biggest chunk, like I said, was my math and theory. This is combined between my undergrad and grad. Now, I mentioned that as part of my undergrad, I wanted to be a software engineer. That influences a big chunk. I learned more about computer architecture and networking. I work for a telecommunication company, so I figured I should learn some networking for my master's. If I didn't do those, it'd just be more math and theory. Now, that's just me, though. What about looking at courses as a whole? So I went to Florida Tech as part of my undergrad, and I went through their course catalog and tried to classify every single one of their courses into what I felt, which one of these buckets they fell under. Now, there's biases there. Course catalogs are imperfect. They don't always offer all those courses. But I wanted to see what that looked like as a broad stroke. Florida Tech, 43% of their courses, I would say, either dealt with math or theory. Yes, there were programming classes, and you programmed in those classes, but the math and theory classes taught you a lot of what are your toolbox, what is the math behind some of the algorithms and the computer techniques you use day to day. Now, most people here probably have not heard of Florida Tech, so let's look at something a little bit more well-known. Caltech, out in California, 50% math and theory. Again, disclaimer, there's some biases here, because it's subjective when I'm going through a course catalog, but I didn't get that many wrong. The overall trend is that math and theory is the big part here. I went to MIT's course catalog, and I went through every single one of their 300 classes that they had in that course catalog. I doubt they offer them all at all times. But once I stripped out all the EE classes, because they combine electrical engineering and CS into one degree, 60% math and theory. A computer science degree is a math degree. I didn't actually realize this as I was going through it, even throughout college. I'm like, I'm a programmer, this is great. No, I look back, it was a math and theory degree. Computer science is not equal programming. And for those of you who have heard this anecdote before, or those of you who haven't, Donald Knuth, a famed computer scientist, used to do these tones of programming. I think it was Knuth, it may have been Dexter, but I'm pretty sure it was Knuth. He said in one of his books, he said, "Forgive me, I have only proven this program to be correct, but I have not actually tested it." And he would actually give out rewards if he found bugs in his program. But mathematically, he'd be like, yeah, I proved that this algorithm is great, but when I actually went to go implement it, we don't actually know. You have to go run it to be sure. It's just kind of a tongue-in-cheek thing. And this leads me to an interesting confessional. I did not know how to program well coming out of a computer science degree. I thought I did. I thought I was a hot shot. Look at me, I got a CS degree. And then I got to the real world of programming and went, I need to learn so much more. And I always put a nice ACD in my slides. Keep in mind, I might be self-taught, and a lot of CS people's code looks like this, where it looks like it's a house being built by a child using nothing but a hatchet and a picture of a house. It looks like a couple arguing at IKEA and someone made random edits to it and compiled it. That's what my code looked like when I came out of computer science. When you self-teach yourself good programming principles, you don't quite realize just how bad your code can be. Throughout my degrees, I never really learned how to write good code. So that gets me into something interesting. In order to become a great software developer, I feel like you have to balance some key skills. There's the practical programming side, where I know how to do the problem-solving specific technologies. I didn't learn the JavaScript framework of the month in my degrees. We were talking back like Lisp and C. So we're talking programming languages 40, 50 years old at this point, not really delving into the new things. So practical programming, didn't get a whole lot of that in my computer science. I got that on the job once I started working. That is critical. If you can do practical programming, I don't care if you have a software engineering or a computer science degree, you can do a lot in your day-to-day job. I feel like software engineering is still important. It's good to have some of those skills. That's when you get to requirements, design, testing, software life cycles, change management, some more of the people and process side of things. And I still think computer science is important. And that's where we get into the math, the algorithms, the data structures, some of that computer theory. I think in order to be a great software developer, you need a balance of all three of these. You can go very, very far with just that top axis. But as you start expanding, you find that you can increase your breadth of knowledge and your effectiveness the more you know. So this talk is focusing on this bottom right piece right here. What is the computer science fundamentals you need to know to help you grow? I'm assuming most people in here don't have a strong computer science background. If you do, great. If you don't, great. You're still awesome. Boot camps. Who here has heard of boot camps? So for those of you who have not, boot camp is popping up around the U.S. and around the world of 6 to 12 week or maybe a few more months of intense topical programming courses. We're talking like possibly 6 days a week, 8 to 12 hours a day in some cases. And the people who come out of there are very, very, very effective at programming. Who here has actually been through a boot camp? Do you mind sharing some of your experiences through boot camp? Would you say that's pretty spot on? Or do you have a different experience?
It just depends on the program. The one that I went to was 3.5 months. I went through 3 different stacks. And so by the end of it, knew like some different languages, but we worked through the same kind of exercises in different ones.
So you're working on real world technologies over there. And so TripleByte, which is, they do some recruiting, they did a study about all the people that they place at jobs. They want to see how do boot camps perform against actual college degrees. They said boot camp grads are better at programming, web programming, and clean modular code over their CS contemporaries or their university contemporaries. However, those university graduates were better at algorithms and how computers work. So a boot camp grad typically didn't get that experience. Now your mileage may vary. You may have heard of a great one that teaches that. But for the most part, this TripleByte, they did not see that. They actually, here's a little graph. I'm going to focus on the yellow and the green, the two right columns for the colorblind among you in each section. The yellow, the second from the right, is university grads, and the green is boot camp grads. And this is TripleByte scoring the people taking their tests, trying to get placed into a job afterwards. How well do they perform? When it came to practical programming, it was pretty much even. When it came to web system design, boot camp grads were much higher, but algorithms and data structures and low-level system design, university graduates excelled at. Now here's my dirty little secret. I've been a software engineer for 10 years. The fundamentals have helped me out of computer science throughout my career, but I have not solved many problems where a computer science background has really allowed me to shine. I've done more programming, just application code, development code. But those times the computer science fundamentals, those computer science ideas could let me shine, really helped out. And that's what I'm hoping to teach you guys today. Just to start getting your vocabulary a little broader and make you guys feel like, you got this. I can understand this. This isn't so bad. And then it'll be on you to take that further. So what can we do to learn CS? And disclaimer, 40 years in a degree is not going to be replaced by 60 minutes in a conference setting or the 45 minutes that we have remaining. So let's dispel that right now. This is not your Pat's one-stop guide to get a degree in 45 minutes. I'm here just to get you the vocabulary and the concepts that you can build upon yourselves. Is this going to be a dry math talk? I sure hope not. I don't like dry talks. I'm hoping for some interaction. I'm going to be asking for some volunteers. If that scares you, you can just stay seated. Also, heads up, I should have said this at the beginning, I am recording this session, so if you're camera shy, don't volunteer. I won't take it personally. I understand. Computer science is all about trade-offs, and the math comes after that. Space versus time. Space versus parallelization. Time versus parallelization. It's typically not the trade-offs like, do I write really fast code versus maintainable code? That's more of a software engineering concern. This is about resource constraints. In general math, we're used to a continuous math spectrum, negative infinity to infinity. With computers, we are bounded. We are finite. Computers can only hold so much space. So there's a whole branch of mathematics, discrete mathematics, that have to focus on how do we express ourselves in this limited space. This leads to resource constraints. We don't have infinite RAM. We don't have infinite hard drives, even though AWS makes it seem like we do at times. We are still bounded by physical real-world constraints. So computer science comes down to trade-offs. How can I decrease the quality of one thing while increasing the quality of another thing? Now, in order to evaluate these trade-offs, we have to know how to measure them. First, some math will come in. It's going to be hopefully pretty simple. If you've taken an algebra class, you can hopefully grasp all the things I have here. If you've forgotten your algebra class, just bear with me. We'll get through it together. So I can give you a whole lot of slides of, oh, here's math, but I'd rather show you of how we start measuring algorithms, because we can't really measure based on number of seconds something takes. I could run I could be sorting a list on my computer. It could take 1 second. It could take half a second in a AWS beefed up server. It could take 3 seconds on my old Windows 95 machine in the basement somewhere. Time isn't useful to communicate between because it's different for everyone's environment. So we're actually going to take a look at something called algorithmic complexity. Algorithmic complexity. So an algorithm, if you aren't familiar with the term, or if you are, you never really know what is an algorithm. It's just a recipe. It's a series of steps to achieve or solve a problem. And we're going to look at a few. Complexity is not time. We may talk about it in the time domain, but let me show you what I'm talking about. We're going to do searching. This is like one of the more fundamental, basic ideas you can get through. Like, I have some data. How do I find information in here? I have a database. How do I look up into a specific row? Anyone who's flown has seen one of these sort of boards up at the airport, list of flights on here. I want somebody to yell out what number flight is going to Singapore. 11. All right. How did you find the number 11? Just as a human. You looked for Singapore, and you probably started at the top or started somewhere on the list and then started going up or down until you find it. Who can tell me where Turkish Air is flying to?
Istanbul.
Istanbul. How did you find that so quickly?
I started at the bottom.
Started at the bottom. So you went up 3 and it was perfect. We're starting to look through all that. As I pick through the sheet, you're looking at the top of the bottom. Let me change this up a little bit. Let's see here. Which flight is leaving at 3:15 p.m.? A lot more people chimed in on that. Why? Why were you so much faster at finding that China flight? It's sorted. That's interesting. This is how we start saying, oh, what is actually different here? Oh. I actually need 5 volunteers. Come on up. You're going to be part of my talk. Just come on up. All right, I'd like you guys to stand in a line right in front of the computer. I have numbers 1 through 5. I am going to hand you each one of them and keep them facing you. Can you guys hear me as I bounce my echo back off here? Can you hear me if my back's turned to you? Okay. Wasn't sure if I had to shadow. So, you probably can see their numbers through here, but that's okay. If I'm a computer, if I don't know where any of this data lies, I have to look through ask every person if I'm searching for data. I'm looking for the number 1. And what I want you guys to do is, as a group, shout out every time I ask someone to flip over a card. Like 1, 2, so like how many times I ask someone to flip over a card. So I'm looking for number 1. Do you have number 1? Flip over your card. 1. Yes, she does. Do you have number 1? 2. Do you have number 1? Nope. 3. Number 4. I found number 1. It took me 5 times for the number of people I have standing up here. That's known as a linear cost. For the n people, I have to search through n people in the worst case to find my number. If I were looking for 6, which isn't up here, I would have to ask everybody in order to find them. Now, I'd like you guys to rearrange so that they're sorted. So 1 starting over here. And we're going to do the same thing. Now we know that things are sorted. So If I know that this is sorted, I'm trusting that these guys can count. I want you again to count every time that I ask someone to flip over a card. So because it's sorted, I'm actually going to start in the middle. Do you have number 1? No. So that's 1. Now I know that since we're sorted, I'm sorry guys, I'm just not into you. I don't care about this data. I know that 1 has to be somewhere over here. Now I could have a 0.9 and 1 for all I know. I don't know what's in my memory. So I'm going to say, okay, I'm going to start here. Do you have number 1? Nope. That's 2 asks. And now I know everything to the right of you isn't needed. Do you have number 1? Yes. 3 asks. What happens here is I'm throwing away half my data each time I iterate through, or each time I ask. I start in the middle. I say, do I have that data? This is called a binary search. And if I don't even have to look here. Whenever I take half my data and throw it away, that's log base 2 of n. So with 5 people, 2 to the what is 5? Is like 2 to the 2.1 or something like that. I'm just going to round up and say 3. At most, if I do this sort of algorithm, at most I have to ask 3 people. Never 4, never 5. If I had 100 people here, the mathematically highest number of people I need to ask is 7. Compared to going through all 100. Thank you, guys. You can take a seat. Give a round of applause for volunteers. There will be more volunteering, so be afraid. All right. So this counts as a linear search going through all the elements. In the best case, the first thing I look for is what I'm looking for. Or the first thing I ask for is what I'm looking for. I don't really care about the best case. We don't live in an ideal world. I care about the average case or the worst case. So on average, if I have n people, on the linear side, that first algorithm, we had to go through 5 different people to find them. In the binary search, when we were throwing away half our data, it was log base 2. So LG is log base 2 of n. So for those of you who don't remember your algorithms, it's like the inverse of an exponent. So if 2 to the 3 is 8, log base 2 of 8 is 3. You have probably heard of big O notation. You probably don't get some chills or like, I really don't know what we're talking about here. That's okay. Big O notation is just what is that upper bound of data, or the upper bound of the shape of my function. So it goes from this 1 element or n elements to big O of 1 to big O of n to big O of log n. There's no difference between these slides other than I put an O in there. There's a lot of math behind big O notation. You don't really need to know it for your day-to-day work. If you're interested, there's plenty of resources out there, but it's dry. It's not great for a conference talk. What you guys need to know is this is the shape of the function. As n grows, as n gets bigger, this is about how many operations I take. Now, when I say operation, I'm not necessarily talking about every instruction in a computer through assembly. I've said every time I flip over a card. That's important too. I'm assuming that flipping over a card is my expensive operation that will dominate things. Now, as another case you'll see me talk about, actually that average case is like O of n divided by 2 in the linear search, because on average I have to go up to half of the array. Average doesn't mean for real world data, it means for perfectly random data, what's the probability that I'll find it. N over 2 is really 1/2 n. If there's ever like a coefficient in front of n, we just drop it, because we're just interested in the shape of the function, not the specific mathematical function it is. So O of n is just a straight line. Whether that's 1/2 n or 2n, it still grows linearly. Let's go back to trade-offs. Someone mentioned it earlier. Why was the binary search faster? It was sorted. That's the trade-off we made. If I can have sorted data, great. Now, sorting is expensive. That's actually going to be our next example. But if you are inserting infrequently to your data, where you only have to sort every once in a while, therefore sort every once in a while, but you're always fetching things, that's where sorting helps out. However, if you fetch infrequently, if you ask someone to flip over that card infrequently, but you're always inserting new people into your data, which requires a whole lot of sorting, you might actually be slower with a binary search because you're sorting more often than you're searching. Trade-offs, trade-offs, trade-offs. All of computer science is, how do I understand these algorithms? How can I talk about them? And then how do I understand their trade-offs? In most cases, there is not one algorithm to rule them all. There is always a caveat. There is always strings attached. So let's talk about sort. I need 6 volunteers this time. Same thing, you're going to be asked to flip cards. Come on, it can be some of the same people. Let's get some new people up here. It's not so bad. Volunteers, was that terrible when you came up here? Just have to stand up here and look pretty. Continue. Okay. Alright. So, 6. 4. Yep, you can show these as 4. May I? One more. Who's going to be brave? Thank you, sir. So, who here is familiar with sorting algorithms? Bubble sort, insertion sort? Okay, I'm going to ask you guys not to answer the question. If I'm a computer, at the fundamentals, I can compare, or you can step out of the projector. As a computer, I can compare 2 elements and I can swap them. Those are like my fundamental operations that I'm looking at. So let's talk about who can come up with how I want, this is 6 through 1, I would like it 1 through 6. What would be a way I could sort that? Think about how you do it as a human, like we did with the searching. Just saying if I can only compare 2 numbers at a time, and then I can swap things or I can move things around, what could you do?
Determine if one is greater than the other.
What was that?
You could compare the 2 and see if one's greater than the other, and then you can swap them.
And so let's go with that one. Let's compare 2. So every time I compare 2 people, I want, again, the audience to count out 1, however many times. So I'm going to compare these 2 fine gentlemen. 5 is less than 6. I need you to swap. That's one comparison. And then I'm going to repeat this. I'm going to compare you 2. You're out of order. Let's swap. I'm going to compare you 2. Let's swap. 3. Come on, guys. Shout them out because I'm going to lose track. I'm going to swap. 4. Thank you. And I'm going to swap. 5. I know that at the end of one pass through n people, I will have the highest element here, thanks to this. This is actually what's known as a bubble sort. Now I know that, well, I still have these 5 to take care of. We're going to do it again. So I'm going to compare you guys. 6. I'm going to have to compare you guys. 7. I'm going to have to compare you guys. 8. Compare you guys. 9. And compare you guys. 10. It's still 10. I have to do the comparison. Now, optimization, I could not have to do that one. I'm going to be a stupid computer for a bit and say I'm just comparing everything from that. So we now have that. Let's speed it up. We know that I'm going to be bubbling these guys up. What number are we at? 11. 11. So, there's a compare. 12. Compare. 12. A compare. 13. A compare. 14. A compare. 15. All right. We're getting into it. Compare. 16. Compare. 15. Compare. Compare. 19. Compare. 20. All right, and then compare you guys. 21. Compare your 5. Compare. 3. Compare. 4. Compare. 25. So we have 6 people. This is going to sound like some right-wing conspiracy theory. 6 people minus 1 is 5. 5 squared is 25. That's actually an n squared algorithm. 5 times 5, so it's n minus 1 squared in this case, what we just did. So we were talking about O of n. If I had 5 operations, it would take me, or if I had 5 people, it would take me 5 operations. Here, if I have 6 people, it's going to take me 25 in the algorithm we just did. If I added a 7th person, it would be 36. If I added an 8th person, it would be 49. That's what measuring this does. I'm going to show you another algorithm. So we're going to do the same sort again. And similar to like a binary search, we're going to start splitting this data set in half and operating on 1 half at a time. So we're going to I'm going to want 6 over here and 1 over there at the end of this. So what I'm going to do is I'm going to position you guys right here, and please separate just in groups of 3. I feel like a magician, like may I have my assistant come over here. I'm going to separate you guys into a 2 and a 1, so separate. I'm going to separate you guys into 2 and a 1. I have not done any compares yet, so we're still counting how many times I compare. Most of the time we're talking about sorting, we're talking about how many compares do I have to do. Now, when I'm looking at just 2 people at a time, I want the biggest number on the left. I'm going to ask you guys, I'm going to compare, and we're going to do a swap. 1. I don't have anyone to compare him to, because he's just standing all by himself. I'm sorry to throw you out on him. I'm going to move on to my next group of 2, and I need to compare 2. I'm going to swap. So this is going to be called a merge sort, because after I break all these people up into pairs, I'm going to start merging them together, because I know for every subgroup, I know that they are now sorted. 2, 1 is in sorted order. 3 is in sorted order. 5, 4 is in sorted order. 6 is in sorted order in their own little section. So now I'm going to merge them together. Instead of comparing this gentleman to everyone else in the line, I'm just going to compare him within his subgroup and the next subgroup. So I'm going to compare 2 and 3. And so who's bigger? 3, I'm going to 3 step over here.
3.
Actually, and then there's no one here in that void to compare against. So that was my 3rd compare. I don't have to compare these guys anymore. They're already in sorted order. I'm now at 3 compares. I'm going to do something very similar to the gentleman over here. I'm going to take a look at both subgroups, and I'm going to say the 6 or the 5. I'm not going to look at the 4 yet, because I know 5 is greater. 5 comes first in my sorting order. 6 is going to come, stand over here. And then I know, so that's 4 compares, the 6 and the 5. And then I'm going to move 5 and 4 up. There's no comparisons needed once I'm there. Now I'm back to 2 subgroups. I broke down into pairs, or 2s and 1s, and now I'm composing them back up into my array of 6. So now I'm going to compare the 2 subgroups of 3. 6 versus 3. That's my 4th, 5th? 5. 6 is greater than 3, so I'm going to need you to stand right here. You guys stay where you are. 5 and 3. That's my 6, so 5 comes here. 4 and 3. 7. And there's no one in this subgroup anymore, so I can just take all of these gentlemen and move them right over here. And voila, I am sorted. Like I said, I feel like a magician when I do this. 7 compares versus 25 compares. 7 is actually on the order in log n. Like I said, you can all take a scale. Take it right here. That was what's known as a merge sort. And that may have looked pretty crazy, you may not have grasped it. That's okay. You don't have to remember that now. But what's important to say is, based on how I changed, how I made different assumptions of my data, I was able to drastically reduce the number of comparisons I'm doing in a search. So if I actually go take a look at that with numbers, on best case for, I'm sorry, I said search, a sort. Best case for a sort, everything's already sorted. I can just say, yep, I only have to go through it once. Now, you may notice I intentionally put them in reverse order. That's because that would show the difference the most between them. For those of you also wondering, if I were to do that bubble sort, but not look at the people I've already sorted, I think it would have only been 12 operations, but that's still greater than 7.
Can we see that in quicksort using Dijkstra's algorithm?
So quicksort, I'll get to quicksort. Hold on. You, sir, may have some CS background. All right. So on average, that naive sort, that bubble sort we did, was quadratic. For n people, we have around n squared operations. And that's going to grow, as n grows, it's going to grow in a quadratic group, the number of operations needed. If I had 100 people, I'm looking at like 10,000 operations. However, that merge sort performs much, much better. It's n log n. I wasn't throwing away half my data, but I was still only operating on a half at a time, and that's where I get that logarithmic benefit as well. It's okay if you're like, I don't know how do I even figure that out? You can do some counting and see if you can mathematically derive it. Or if you're using a well-known algorithm, just go Google it. It's all out there. If you're devising your own, that's going to be the thing I can't teach you just in a 45-minute session. But this should give you those fundamentals. So what was the trade-off there? Because like I said, there's always a trade-off. That merge sort, I don't know if you guys noticed, I was asking people to step forward whenever I was pulling them out of their array. Merge sort requires extra space to pull that off. It actually requires just as much space as the size of my input. So for 6 people, I had to have enough room for 6 people to step forward. So merge sorting on large data sets might not be tenable. If I have to sort a gig of data, that means I need an extra gig sitting around for me to go throw my temporary results in there. There are in-place merge sorts that are very, very complicated, and I can't do that with just people that avoid that, but you start trading off other things with that as well. Now there's also a quick sort. You mentioned it back there. You might be thinking quick sort. Quick sort should be quick, and it is. It doesn't do that extra space allocation that a merge sort does. So matter of fact, so the best case and average case are the same. What will actually happen is that we talked about coefficients. Quick sort on real world data will perform faster than a merge sort. It's typical just because it's not pulling in all that extra allocation. But that worst case is actually even worse. In that reverse sort, or if you are reverse sorted and you're trying to reverse that sort, a quick sort will actually take n squared algorithm, just as bad as that naive sort earlier. There is no one algorithm to rule them all. And people create crazy sort. Python has something called tim sort, named after one of the Python developers. C++ under the hood does something called an intro sort, which is a quick sort with the naive sort for small data sets. I'm not going to bore you with those details. Just understand there's not always one algorithm to rule them all. There's always trade-offs. How much does this really matter? I've been talking to you for 20 or 35 minutes now. How much does it actually matter what these big O of N's are? Let's do a thought experiment. So this is a graphic, easier visual. That O of N typically looks like a straight line. As my input size grows, this is how many operations I need. So for 100 input, I need 100 operations on average, or some factor of 100. N squared is this red line over here. N log N is this yellow line. We're interested in how N grows. As my input gets bigger, how tenable is my algorithm? So here's my thought experiment. We're going to be looking at two numbers, n equals 100 and n2 equals 1,000. We're going to see what these different algorithms look like compared to it with some actual numbers. I'm assuming that each operation takes a nanosecond. That is intentionally simplified. Not every operation takes a nanosecond, but it'll help us talk about how these grow. So O of 1, the simplest. It's constant time. No matter how big my input is, that's how long it will take. So Grace Hopper used to do this. She had an 11.82-inch piece of metal, and she would use it to talk about the speed of light. Because she was a rear admiral in the Navy, and she'd always be asked, why does it take so long for my computers to talk to a satellite? It should be the speed of light. That's instantaneous, right? She'd hold up something about the size of a ruler and say, this is how far light travels in a nanosecond. There's a lot of these 1-foot pieces of metal all the way up to that satellite. That's why it takes so long. Similarly, I'm going to use that as a baseline. We're going to be talking about how much time does it take light to travel from one place to another as n grows, and as our algorithmic complexity grows. So constant is the same. No matter how big n is, it's always going to be about the length of a ruler in terms of how fast light can travel. Log of n, like our binary search. So for n1 equals 100, we're looking at about 7 nanoseconds, or about the size from Shaq's head to Shaq's toe. For those of you who don't sports ball, that's a very famous basketball player, 7 feet tall, big man. When n is 1,000, we're looking at 10 nanoseconds, or about 3 feet higher for Shaq to dunk on a basketball hoop. So we're going to start diverging just with a factor, so n is 10 times larger, but we don't see a 10 times increase in how long it takes for our algorithm to run. O of n, this was our linear search, that very first search we talked about. So O of n is, n1 is 100. It takes about 100 nanoseconds, if every operation is a nanosecond, or about the time it takes the light to travel from home to first base on a baseball field. When n is 1,000, it's now the time it takes to go to the bar across the street. It's starting to grow. O of n log n, that really nice sort we were doing, though it seemed a little bit faster, that merge sort that seemed complicated. When n1 is 100, we're looking at 700 nanoseconds. That's the amount of time it takes for light to travel from the top of Golden Gate Bridge to the basement. When n2 is 1,000, we're looking at my computer turning off. Magic. About 10,000 nanoseconds. The length of the national, come on computer. Okay, let's hope that stays. 10,000 nanoseconds, the approximate amount of time it takes to take across the National Mall, about 2 miles. Let's unplug it, plug it back in. Let's see if that works. Okay. One moment. All right, let's everyone cross your fingers. is where the fun starts beginning. We were just talking about national. Now compare that back to Shaq and the basketball game. From a difference of 3 nanoseconds to 9,300 nanoseconds, just because I went from the log n algorithm to a n log n. Let's talk about quadratic, O of n squared, naive sort. With 100 elements, we're back to that national model. But with 1,000 elements, I'm now looking at a millisecond, or about the time it takes me light to travel from Huntsville to Memphis. The more n grows and the more complex these algorithms get, the more of a divergence you're going to see between these. And you want to flip the table when you start running into things that are really slow. O of n cubed, we haven't talked about this, is cubic. If n1 is 100, we're back at that 1 millisecond range. When we get to 1,000, well, we might as well be on it. It's infuriating slow when we start talking about cubic algorithms. Your head wants to blow up because you're like, well, I'm just going to wait for the heat death of the universe before this thing finishes. O of n factorial. I don't even have like realistic white numbers here because at n1 equals 100, I'm looking at a 9 followed by like 145 zeros. That's big, longer than it takes light to travel across the observable universe by like a factor of 100, like multiplied all that. When we get to 1,000, I don't know. Factorial algorithms are bad. That's what you can take away from this. If you have a factorial algorithm, if you have more than 20 elements, you're probably going to wait billions of years.
How can you even write an algorithm that's so bad that you get it in factorial?
So how can you write an algorithm that's so bad? Getting all the permutations of a sequence is a factorial algorithm. There are certain things that are mathematically the best you can do is factorial. And so for those of you like 5 factorial is 5 times 4 times 3 times 2 times 1. Let's say I had a string that was 5 characters long, I wanted all permutations of it. So I look for every 5 elements, there's one of 4 elements that can follow that. And for each of those 20, there's one of 3 elements that can follow that. And there's one of 2 elements that can follow that. 5 times 4 times 3 times 2 times 1. Permutations are factorial, which is why we can't do permutations on large data sets. Not in the naive way. Mind blowing. This matters. This matters. And we talk about hundreds and thousands. What about millions and billions? Facebook has like 2 billion users. Do you think they want even an n squared algorithm when they have to go do something on every one of their users? No, they're looking for those logarithmic algorithms, log n or n log n. This matters. And if you want your company to be successful, you're probably growing your input size somehow. More data, more users, more interactions, more transactions, more sales. If your algorithms are complex, n squared, n cubed, as they start going up in that spectrum, you're going to have a bad time. So how can we improve things? Trade-offs, 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 trade-offs. That's what computer science is about. You can sort things. That's an example we saw with the search. Maybe you can make some assumptions about your data if it's sorted. It's nice. You might have extra space lying around. This space is cheap. What's another terabyte? Maybe you can do something like with a merge sort and just grab some more space. Or maybe your data structures can help. We haven't talked about data structures yet. Let's get into that. So when we talk about data structures, we typically think about CRUD operations. Create, retrieve, update, delete. Updating and like retrieving are pretty much the same thing to me. So I'm interested in how do I insert into a data structure, how do I delete from it, and how do I retrieve it. A data structure is just how you lay out your data in the memory of the computer. So we're going to take a look at arrays. I need 5 volunteers. 1.
Going back.
2. Come on, guys. It's okay if you've done it already. Come on. I know everyone's regretting their life choices coming to this talk. All right, how about just one more? How can I just get one? There we go. Can I, guys, if you don't mind, standing right over here, just so we're along with the video. So an array is contiguous memory. That means that when I allocate an array, I can be guaranteed that these gentlemen are always right next to each other. If we think of a memory layout in a computer, it's really just different addresses. Each person represents an address. If I want a new array, I can just hand that data over there. So there are 2 separate arrays, an array of 1 and an array of 3. But you get, in terms of memory layout, these guys are all right next to each other. Now, actually, yeah, I'm going to remove this from you real quick. Don't feel too bad, don't get it back. If I want to insert something into the array and I have extra space, Great. If it goes at the end, that's fine. Now, that only took one operation. Let's count how many times I have to move cards around. I moved one card over here. Let's take that back. Now if I want to insert the number 1, but this is sorted, what do I have to do? I have to go to the beginning. I'm going to say I'm going to hand this to you, but you can only hold one card at a time. So you're going to pass your card to the right. So that's one move. You're going to pass your card to the right. We have 3 moves, 2 moves to shift it down, 1 move and 1 move for the actual insert. So in terms of inserting in the beginning of an array, I might have to shift the entire array forward because all that memory always has to be right next to each other. And if I want to insert the number 4, I don't want to hand it to this gentleman here because he has a different array. That's someone else's data. This is how a lot of security, like vulnerabilities happen. Someone goes past their array and overwrites it with willy-nilly data. This is how Heartbleed worked on SSL, like that SSL attack, is because an array got overrun into someone else's memory. So if I want to insert 4, I need to go ask these 3 gentlemen to move somewhere else and call up a 4th volunteer to find that space, which means I have to do a copy. Even though I'm inserting at the end, they have to hand off to that new space. For arrays, inserting the beginning is great. Inserting the end is great. Inserting the beginning or middle, or needing to shift because I need to reallocate my array, is slow. It's linear. I have to touch every element of that array. Now, what will also happen is I can advance. When I want to say I'm going to start with this gentleman here, and I want to move 2 spaces forward, I don't have to look at him. I can just walk right by him. You're important. Don't feel bad. And just go right here. That's nice. That's not too bad. That's what an array looks like. We're talking about contiguous memory. And so if I would pull this up, you'll actually see if this is how a memory layout of a computer where like all your variables are stored, each color might be an array. And there might be a lot of free space. But what we're showing here is this 2, 3, 4, 5 in red. And I didn't like the orange card, so I just printed it out white. Bear with me. And the new array showing up there. All that memory has to move in one chunk or the other. That's what, because when it's contiguous, that's what lets me jump over people. All right, gentlemen, you may sit down. You may do. Thank you very much. So arrays are one factor. There's also this non-contiguous memory. I'm going to show the picture first, and then we're going to do volunteers. Non-contiguous memory looks like this, where it's all over the place. This is the head of my linked list. It doesn't mean that the rest of the list is right here. What I have is a value and an address, that A0. If I go down to address A0 in the bottom left-hand corner, it gives me the next value and the next address. It's linking a list across memory. And then that will take me to address 90, which will take me to 92, 94, which will take me to 75. I'm using the 0 to say that's the end of my list. So I need 4 volunteers, and you don't have to come up. We're actually going to do this while you're in your seats. So just raise your hand if you'd like to be a volunteer, the luckiest volunteers in the crowd. There we go. So number 1 is coming over here. Do I have 3 more people who just want to hold a card? 2. Should I give you 4? Actually, no. I will give you 3 and 4. All right, so everyone's going to have to turn around to see this. My apologies for those on the recording. I'll try to narrate this best as I can. So number 1, may I have you point to number 2? You need, this is the cost. You have to hold your arm up for this. 2 point to 3, and 3 point to 4. If I want to insert 5, all I'm going to do is say 4, do you mind pointing to me? Bam, that's all that it took. I just allocate my memory wherever I am in my computer, and I just need my 4th element to point to me. If I want to insert this 5 in the beginning, let's ignore sorted for now. All that I have to do, you guys stay pointed the way you are. I say, I'm now the beginning, look at me, I'm the captain now, and I'm just going to point to number 1. It doesn't matter that we're all next to each other. We can just know our points. The cost is I have extra memory to store the point. Even if I wanted to insert 5 between 2 and 3, here's what we're going to do. I'm not going to even look at 1 and 4. 2, do you mind pointing at me? And I'm going to point 3. Just by updating like 1 person and inserting myself, I was able to insert in the middle without touching 1 or 4 and changing their pointers. That's what non-contiguous memory is. Thank you, gentlemen. Once you know, I mean, these are really the cores of what most data structures are built off of. Once you know contiguous versus non-contiguous, oh, actually, let me back up. Just real quick for reference, finding things within there, you still have to iterate through the list. Advancing by some number, in the linked list example, I would have had to start at 1 and say, who are you pointing to? Number 2, who are you pointing to? And walk the whole list until I found number 4. Iterating is still O of N. There's actually a cost there that I'm going to get to. Inserting an arrays, inserting at the beginning and the middle, slow. I either have to shift the array or reallocate it. In the end, if I reallocate it, it's still constant because there's a mathematical property where it's constant on average. If you want to learn about amortized analysis, come find me afterwards. The linked list is fast to insert. It may be slow to find element in the linked list, but it's fast to insert. And a delete is the same as an insert as far as I'm concerned. There's something interesting here though. I had a little star on my cache locale. So most people's computers have a cache. I need one volunteer to come up here. This is the last volunteer of the day, so if you want to have your time to shine, well, that's my talk. Someone else might ask you a volunteer, I don't know. Can I get one person to come on up? And then, now that I've made him come up, I need one more volunteer to stay seated. All right. I am handing the numbers 1 through 4 to the seated gentleman in the crowd. All right, Jeffrey, what I want you to do is no matter how dramatic I make this, you only have a walking speed, your normal walking speed, okay? I'm going to be asking you to go get memory from my RAM. This gentleman is my RAM, you are my cache. You may hold 2 values at once. Can you go retrieve number 1 for me, please? I said normal walking speed. Goes and retrieves number 1 for me. So as this processor, I'm asking for a value. My cache is going to go to memory, go get it. Said I'm going to use it. I said, oh no, that's not the one I want. You mind getting 2 for me? Oh man, I've got 8 minutes left. Time's an essence here. Time's an essence. Time's an essence. Go, let's go, let's go. I can't change the speed of light. We're talking about electrons here. You know, I think I liked 1 better. No, you have 1. Yeah. 1. I didn't have to walk there. You know, no, I like 2 better. When I'm interacting with my cache, it's like the bank teller who has all the money in the drawer. They don't have to go to the vault to get every $20 bill. They can have a local cache of cash that they can grab. But whenever I don't have something in my cache, he has to walk to my memory. That's it. That's all. Just helps you see. It's slow to walk there. And you might be saying, just how slow is it? How slow does a cache read things? Well, let's talk about the array first. What happens is when a cache reads from your memory, it doesn't read just one value at a time, it actually reads an entire line of data at a time. So look at this blue array up here that starts in the 20s. When I ask for that first value, this whole entire array is populated, or I'm sorry, this whole entire line is populated into my cache. Maybe not the whole array, but enough elements in the array. So when I ask for the second element of that array, it will already be in cache. When I ask for the third element in the array, it will already be in the cache. That's great. This is an idea of cache locality. The data you're operating on typically is data you last accessed or data that is right next to other data that you've accessed. If you have a whole bunch of variables in a function, if you access one variable in a function, you're probably going to go access the next variable in the function. And so you typically have them laid out as such. Compare that with non-contiguous memory. So we're going to do the greens on this one. So this A01, I ask my cache to go get all this data from the memory, and I read that number 1 that says, oh, I need address A0. A0 is not in my cache, which means I have to go make another trip, walking all the way back into the crowd to find that. And then when I ask for the next element, I have to walk all the way back into the crowd to find that. Caches are small. They can't store a lot of data. They start aging things out. So it might be that they forget about things by the time you need them again, because they have a finite size. There are real-world constraints here. And I have one final cache. So when I get this line of my linked list in the cache, I said I need address 92. That's in my cache. 94 is in my cache. 75 is not. I need yet another cache access. How much does this matter? Speed of light actually really does matter with this. It's from Peter Northridge. Lots of data here. I'm going to highlight 2 things. Fetching from your L1 cache is about half a nanosecond. Now this is making a bunch of assumptions. The order of magnitude is more important than the size. Fetching from main memory, my RAM, which is the gentleman in the crowd, is 100 nanoseconds because of the speed of light. Your main memory, your RAM, is further away than your cache. Your cache lives like right inside your processor. Your RAM is maybe a few inches away on your motherboard, or maybe you're just an inch away, or something like that. That matters when we're talking like micrometers versus like centimeters. So there might be a 200 times slowdown whenever you have a cache miss. There's actually tools that will tell you how often you miss caches. So while linked lists are great at inserting, deleting, removing right in the middle, they pay for it because they're not well suited for your computer architecture, which is typically with a cache. Once you understand these data structures, you can start applying data structure semantics on top of it. You can talk about queues, like a line of people at your local Taco Bell. The first person in the line is going to be the first person served. You don't want the last person who shows up to be the first person served. First in, first out. You can do that on top of an array or linked list. You can have a stack, or like maybe a stack of pancakes. The last pancake you put on is the first one you eat. You're not going to pull out the bottom pancake unless you're a psychopath, sorry. You take out the top pancake and you eat that top pancake and then you eat the next one. The last pancake and is the first one to go out. We can talk about things like hash tables where you have constant lookup. This is a really, really cool thing built on top of arrays. You can't build it on top of linked lists, but because it can take advantage of contiguous memory, it can create a lookup structure that gives you constant access. We've talked about linked lists. We've talked about trees. Oh no, we haven't. So trees is like the binary search. This is like a linked list, but every node has 2 children, and that cascades down. You see that a lot in logarithmic algorithms. Or graphs. Driving from Huntsville to Memphis, the GPS can be displayed as a graph. And that will give me a whole slew of algorithms that I can use to find out what's the shortest route between here and Memphis. And so on and so forth. Even programming languages matter. Lua is built off of tables, which is a whole bunch of arrays and hash tables. Lisp is all built off linked lists. You might have been thinking, oh, I thought those might have been slow in cases, is so that Lisp can get its functional programming performance when copying immutable data structures. C++ lets you pick which data structure you want, whether you want a list or an array, and all the other terms that go through C++. I'm an everyday C++ programmer, so I feel like I'm going to bash on that. It's all about trade-offs. What are the trade-offs you make for the decisions you have? And so on and so forth. Look, you guys can Google just as good as I can. I can give you the fundamentals. This isn't scary. It's just how I measured how complex an algorithm is. If you're interested in this, go Google algorithms and take a look there. Where does this leave us? Understand algorithm complexity. Understand that performance is a feature. Not every piece of code has to be fast, but some of them absolutely have to be. And when you are looking at that piece of code, understanding algorithm complexity and making your algorithms go from like n squared to n can make a much more improved difference over, oh, I just removed like 3 variables from this calculation. It's the coefficient versus how the function shape is. Remember your data structures, contiguous versus non-contiguous, and all the semantics that can be built upon that. And trade-offs. I mean, I've had this slide 5 times in. Trade-offs, trade-offs, trade-offs. That's really what I took away from my computer science degree. You don't always need one. You don't always need a computer science degree. But that doesn't mean the information that you learn from that degree is not important. For those of you who are interested, we have 1 minute left. Get this back to full screen. Here's a visualization of quick sort, heap sort, merge sort, radix sort. You can find visualizers all on the web to see how things go. You know why I said quick sort was fast? Well, this data was mostly reverse sorted, so it's actually the slowest of the bunch. So this is actually sorting colors left to right. You can see, let's see here, insertion sort, which is very similar to the naive sort we did at the beginning. The bubble sort, where we're sorting and we're seeing values bubble all the way up. It gives you an idea of how to visualize these algorithms. Most algorithms have some really cool visualization options out there. So you can find me on Twitter, @ViewForever, if you ever have any questions. I have a blog that I update maybe once a year, so you don't need to go there. But if you have any questions, chat me in the hallways, come tweet at me. I'll be happy to explain things or refer you to other resources I found and I just don't know. And thank you guys. Thank you to our sponsors from DevSpace. Thank you guys for coming to my talk. I hope you guys have a great 2 days.